Hey there, Science 2 kiddos. Just going to use these slides to review content from Hewitt, Chapter 11.2 and 11.3, all about states of matter and phase changes. This first little diagram here is just a joke. It's a graph comparing time and degrees Celsius measuring temperature for a cup of tea. The joke being that tea is either way too hot when you first heat it up and then suddenly becomes way too cold if you decide to wait. You only get a fraction of a second where it's actually a reasonable temperature. So temperature and kinetic energy is what we're learning about in this unit. You've got to understand that kinetic energy is just the energy of motion. Anything in motion has kinetic energy. This is different from potential energy, which is just the energy of position. Bicyclist is the best way to describe this, right? This bicyclist waiting at the top of the hill right before he or she goes down the hill would have potential energy, and then in this moment of motion going down the hill actually has kinetic energy. I want to zoom in even further and think of it on a molecular level and looking at how the elements and atoms that make up all matter are also moving and have kinetic energy. Temperature is a measure of that. So I know it's weird to think, but think of temperature as the average kinetic energy of particles in a substance. So if you're looking at water and taking its temperature, you're actually taking a measurement of the average amount of kinetic energy, the average amount of motion that those water molecules are in. And so something that's very hot, all the particles that make it up on average are moving very fast. Something that's very cold, all the particles that make up that substance on average are moving very slowly. Now, something that's kind of weird to think about is that anything that is absorbing heat, so any reaction or something like that that absorbs heat, when you touch that, it's going to feel cold to you because it is removing heat from your finger, right? We call this endothermic. Any reaction that does this is called an endothermic reaction. But remember, if it's absorbing heat, it's actually gaining energy, right? It's gaining heat by absorbing it, but it's going to feel cold to you because it's removing that heat from your finger when you touch it. Vice versa, anything that's releasing or transferring heat is going to feel warm to the touch, right? Because it's releasing that heat into your finger. We refer to this as exothermic. Again, think of that as exo meaning out, energy out, right? But it is releasing energy. It's actually cooling down, becoming colder, but it's going to feel warm to you because it's releasing energy into your finger. So again, something weird to kind of wrap your mind around, but that's something we'll come back to a little bit later. The states of matter I'm hoping you're familiar with are solids, liquids, and gases. There is a fourth state called plasma, but I'm going to focus on those first three. Solids have the lowest kinetic energy, as you can see in this diagram here. They're not standing perfectly still. The particles that make up a solid are vibrating in place. That's why they have these little shake animations there. They will take any shape, right? If you have a rock in a container and pour it out of the container, it will maintain that same shape. They have very strong attractive forces between them. That's why they're so compacted together, and they're so compacted that they cannot be compressed any further. And what I mean by that is that you cannot shrink the volume. Now, yes, you can crush a rock, but if you were to crush a rock into that sand and then continue to crush that sand and dust that you've crushed it into, you wouldn't actually be able to change its volume because particles are already as close together as they're ever going to get. Liquids are actually very similar to solids, so that's something I want you to put in your minds right now. Solids and liquids, associate them with each other. They have a little bit more kinetic energy. Think of the particles as sliding past each other, right? So that's why they have these little animations, but they're still compacted together. They will take the shape of whatever container they're in. So if you have a glass of water, it will take the shape of the glass and then pour it out on the table. It will flatten out over the table. Again, it's drawn down by gravity. If you've seen liquids in free fall, right, they form little perfect bubbles. And that's because, again, there are some attractive forces between the molecules. Water, especially due to its polarity, right, you get these drops like that because they're very strong attractive forces, even in liquid state. And they cannot be compressed. Technically, they're slightly compressible, but for our understanding, we're just going to say, again, they're so compacted together, they can't really be compressed. You can't reduce the liquid. That's how hydraulics work, right? We use that in machinery. We put liquids under pressure, and they exert that same amount of pressure onto something else because you can't really change their volume. Gases are very different from liquids and solids, right? They have incredibly high kinetic energy. That means that their particles are spread far apart and are moving very, very fast. They take the shape of whatever container they're in completely, right, regardless of gravity, though, again, gases will respond to gravity. That's what holds our atmosphere to the surface of our planet, but otherwise they are kind of bouncing around freely. They have little to no attractive forces between them, and they can be compressed. They have so much empty space between the molecules that if you're able to capture a gas in a container, you can shrink or expand its volume, and that generates what's called pressure. There's lots of cool stuff we can study with that, which we'll get to when we learn about gas laws. So here's a little summary table, just showing you the 3 states of matter and basic trait or characteristics that I went through, right, from kinetic energy levels to whether they could be compressed or not, and that sort of thing. So this is a good thing to refer back to for review. Here are the classic images that you often see, and again, I just want to emphasize, think of solids and liquids as being very similar to each other, and gases being in a very different spectrum, right? If you were to take a kinetic energy scale, almost, where you've got low kinetic energy and high kinetic energy, I'm not really going to try to fit a scale in here, but solids and liquids would be very closely associated with each other. Gases would be completely different. They have so much more energy and motion going on. Now, you need to be familiar with what we call the phase changes. I'm not going to write them out completely here. You'll see other images that refer to them, but hopefully you're familiar with the idea that going from solid to liquid is referred to as melting. Or you'll also sometimes hear the word fusion, which I know is confusing, but fusion is also another way to refer to melting. Liquid to gas is collectively called vaporization. I'm just going to write, let's spell it out. So that includes boiling and evaporation, which are actually 2 different things. We'll get to that a little bit later. The reverse of that, going gas to liquid, is called condensation. I'm just going to shorten that. I'm not going to try to write that whole thing out. We'll see it later. And then liquid to solid is called solidification or freezing. You can jump directly from solid to gas. That is referred to as sublimation. Something you see dry ice, carbon dioxide do a lot. And the reverse of that, gas to liquid, is called deposition. Like you're making a deposit in the bank. Now, an important thing to understand is what's happening with the energy, okay? As you go from solid to liquid to gas, as we have talked about in terms of kinetic energy, you are gaining kinetic energy, right? Higher kinetic energy as you go from solid to liquid to gas. And the reverse is actually lower. You're lowering the kinetic energy, right? So in other words, going from solid to liquid to gas, energy is being absorbed, right? Those processes are going to feel cold as part of the process to the touch. And then your reverse, gas to liquid to solid, is releasing energy to become colder. This is why the back of a refrigerator, if you ever touch the machinery behind a refrigerator, it's incredibly hot because you're actually removing heat. You're cooling things down. So the processes that require heating, right, a gain in kinetic energy, are melting, again going from solid to liquid, and vaporization going from liquid to gas, and sublimation, which is the direct jump from solid straight to gas. And again, heat just adds more and more kinetic energy, and it pretty easily distributes to all the other molecules gradually, right? And so cold is really close together, hot is going to be spreading them apart more and more until they escape. And you'll see this animated in a PhET simulation we'll be working on in class. Cooling is the exact opposite direction. You're decreasing the kinetic energy, so solidification, going from liquid to solid, condensation, going from gas to liquid, energy is being removed, right? Molecules are slowing down in their motion, compacting together again, being attracted to each other more. Deposition is just going straight from gas to solid. And so that's what happens when like frost forms, technically, oftentimes. You can see deposition in very cold places if you have something or something very cold. Condensation is happening inside of a Coke can, right? That's where you have water vapor in the air, suddenly gets cooled down when it comes in contact with a cold can and will form a liquid on the side. The can isn't actually sweating, though I know that you hear that referred to sometimes. So again, here's a nice little sort of general summary of the different states of matter and the phase changes, as well as, again, I like this kind of diagram clarifying what's going on with the heat and what's actually happening with the molecular motion, the kinetic energy of the particles. Now, temperature is not the only thing that can change states or cause phase changes. You also have pressure, and this is something we're going to get into a little bit more when we talk about gas laws. But you can have what's called a phase diagram, which is showing the states of matter, but it's at what temperature and what pressure. So we tend to talk about the states of matter assuming that we're at sea level standard pressure, right? Which is usually like one atmosphere or 101.3 kilopascals. But pressure can obviously change. You can have higher or lower pressure situations. And so you can see that anytime you've got very high amounts of pressure at very low temperature, that tends to be solids. In the middle tends to be liquids, and very high temperatures, very low pressure tends to be gases and or vapor. The triple point is a very interesting thing. All forms of matter have a triple point, and it's the exact temperature and pressure at which you would get all three states of matter at once. So you would be seeing freezing, boiling, condensation, evaporation, or condensation, vaporization, all happening at the same time. This video right here, which I'll show in class, will kind of show that. You can check that out. So not all phase diagrams are the same, right? This is for water. This is for carbon dioxide. You can see the carbon dioxide tends to likes being a gas most of the time, and you have to have extremely high pressures to get it to be in liquid form at a certain temperature as well. And so it kind of determines the state that we tend to find them in on the surface of our planet and the way we interact with them, right? Carbon dioxide is often a gas. Water, though, we can see is both liquid, solid, or gas, depending on slight changes. So all the phases are shown, and again, I'm not going to take the time to actually fill in all these boxes here, but that will be something you can do for homework. This is showing you that. Again, anytime you've got very high pressure but very low temperatures, that's going to be solid. Things in the middle tend to be liquid, and anytime you've got high temperature and low pressure, those are your gases. And so there are your same phase changes showing you, again, these are just the borders of where these changes would happen, what temperature and what pressure. And again, you have that one point right there referred to as the triple point, where you could get melting, freezing, vaporization, condensation, sublimation, and deposition all happening at the same time. It's pretty chaotic looking. Now, all forms of matter also have what's called specific heat, which is basically just a measurement of how easy it is to heat up something. Specific heat is symbolized with the letter C, don't ask me why, and it's defined as the amount of heat needed to raise the temperature of 1 gram of a substance 1 degree Celsius. It's based on water, so water is kind of our basis for all this. So water sets the 1, right? It takes 1 calorie of energy to heat 1 gram of water by 1 degree Celsius. That's the basis for this. So here's a table showing you the different specific heats. Notice there's 2 different units. This is in joules, this is in calories. We'll be learning how to convert between these. But for your general understanding right now is just to understand that anything that has a low specific heat means these heat up quickly and easily. And it's not surprising that you have metals down here, right? Silver, iron. You know that if you leave a metal spoon or even an electrical device like a phone or iPad on a table out in the sun, it warms up very, very fast because the metals that it's made of have a very low specific heat. They will heat up quickly. Water, on the other hand, right, heats up slowly. If you've cooked anything, right, it takes a long time to boil a pot of water, and it takes a lot of energy. We'll just say lots of energy. You need a lot of heat to change the temperature of water. And so this is actually pretty important in terms of our planet. We've learned about how the oceans, currents, and wind help determine weather and average temperatures. And so if you look at water has very high specific heat. The oceans are very good at absorbing a lot of that heat without actually changing their temperatures. Even though ocean water stays relatively cold, it's absorbing a lot of the heat coming from the sun, the solar radiation. And so it's not surprising then that if you look at our state here, California, look at the average temperatures in these places that are on the coast. Look at San Francisco, look at Santa Barbara, and now compare that to Barstow. Or, I mean, Death Valley is an extreme example, but even looking at Blythe or Sacramento, you'll notice that temperatures tend to be a lot cooler on the coast, and that's because of the vicinity to the ocean, right? The Pacific is sort of the air conditioner for the western coast of our state, but once you go inland, you see much higher temperatures because they're not as close to the water. Okay, hope this was helpful. You'll be reading the chapter